We have formulated weighted least squares. We have seen that we can favor certain data points over others. We formulated it and we derived it, and very nicely, all it required was inserting a matrix, a diagonal matrix, into the former least squares estimation. And so now let's do what we always do, which is let's go ahead and implement it. So I'm going to give you a little bit of scaffolding in the code. I'm going to ask you to write some code to fit a second order polynomial, same as we did before with the least squares, to n data points using weighted least squares. Each data point should be weighted by the square of its distance from 0. So what I mean by that is only looking at the x-coordinate. What is the distance of the x-coordinate from 0? Don't care about the y. And please square that so that points that are further along, either negative or positive from the origin, will be weighted more than points near the origin. And I'm just reminding you here that in order to compute a diagonal matrix, you should look at diag. Here's the scaffolding for the code. Import the library. This is the same as before. 20 data points. You can play with this if you want. Generate random x values along the horizontal axis. Generate the corresponding y values following a parabolic model. Here's x squared, here's x, here's the constant term, and then add a little bit of jitter or a little bit of noise. Your code goes here. This is the display code. Your code, as before, should output the vector u, that is a 3x1 vector corresponding to the square term, the linear term, and the constant term of the parabola. So go ahead and stop the video, pause the video, work this out. It should only be about 3 or 4 lines of code, and then when we come back, I'll show you my solution. All right, I hope you got that. Let me start by looking at the visualization. So the yellow, of course, are the underlying data points here, and the fit is shown in the cyan color. And what you notice here is that on either end of the parabola, these data points here are extremely well fit to the parabola, whereas I get towards the center, not so much here. You can see that the data points are way lower than the parabola. Why? Well, because I favored these values significantly more than I did, in fact, by the square of the distance, and I did that intentionally so you could see the difference. Let's go look at the code now and make sure we understand it. All right, this part is exactly the same. I've got my x matrix, which has x squared, x, and 1 packed into the column. So this is an n by 3 matrix. Now I've just got to compute the diagonal matrix and then do the weighted least squares. So I'm going to compute the absolute value of x and then square it. And now that I look at that, there was absolutely no reason to take the absolute value because the squaring was going to take care of the sign there. And then I'm going to build a diagonal matrix, np diag, with that w along the diagonal. So every element of that diagonal corresponds to the square of the distance of the x-coordinate of each data point relative to the origin here in the center. And now it's just weighted least squares. So I'm going to take the inverse of x transpose times w times x times x transpose times w times y. That's my weighted least squares. I pack that into u, and then I just do a little bit of plotting. And again, you're responsible for figuring out what the weights are. The weighted least square says, you tell me the weights, you tell me what the data points are, and I will do a weighted least square. In many ways, weighted least squares is a generalization of least squares, and we could argue, as I said before, that it's all weighted least squares. It's just that the weights are all equal. And so it's good to remember that not all data points are necessarily created equally, and we can either because we care about certain parts of the domain or because we have trust in more data points, can treat the data that we are ingesting differently and selectively and use that in our model fitting.